Hi, I'm Craig Walloch. I'm with CMHA. It's a fairly new organization name-wise. If you're familiar with NCMA, the black guys, and ICPI, the paver guys, they were together back in the 90s. They split apart, and 2 years ago they came back together, threw out half the letters, traded in other ones, and came up with CMHA. So we basically represent all the manufactured dry cast products. So I'm going to talk about carbonation of CMU. Now, the rate of carbonation of what we call in our business regular wet cast concrete has been studied and modeled, and there's a fair amount of information on it. The rate's generally fairly slow, depending on number of factors, composition, curing, permeability of the concrete. The rate of carbonation of dry cast concrete really hasn't been studied. So we undertook some research back in 2020 to start taking a look. This is preliminary research in the sense that, we got block from a wide variety of producers. We ended up with 9 sets from across North America that we evaluated. Now, just give you some idea of CMU, that's the term we use, concrete masonry units. They're dry casts manufactured zero slump with vibration. I don't know if you've ever seen it. It's a mix that is dry. It won't slump. It comes on a feed into a mold, gets vibrated down. The mold lifts off. It's got enough integrity to move down the line and get cured. Okay, people call them concrete or cinder blocks. Most common shape is a 8 by 8 by 16, 20 by 20 by 40 centimeters. And one of the unique things about it, it's only about 50% solid. And the webs and the face shells, the elements are only an inch and a half, 25, 40 millimeters in thickness. That's important for us as far as uptake. These thin elements, as well as the more porous structure of the concrete, right, differentiate from wet cast and results in a significantly higher natural carbonation rates, especially at early ages. So this gives us some idea of the structure. We look at it, ready mix. We really don't have interconnected voids. We have air-entrained bubbles, right? There is some porosity, capillary porosity of the paste and mortar fraction, but really not a lot of interconnected stuff. In dry cast, we have an amazing amount of interconnected voids, okay? Those cause us all kinds of headaches for water penetration, for efflorescence, and, a lot of stuff you guys don't have to deal with, we have to deal with. But in this case, it helps us out with carbon sequestration because we have this open structure that the CO2 can get to. As far as a typical block, cementitious content's 8 to 15%. A regular gray block's going to be 9%. Aggregates, water, don't get fooled by the water number. It's 5 to 8. That's 5 to 8 of total moisture in the system. Block guys do not care about SSD. We are not making volumes and selling cubic meters of concrete. We're selling widgets. So a lot of them don't even know what it is. But, the water cement ratio is probably typically 0.32 to 0.35 if you actually figured it. And then admixtures. But even though that the cement's a small proportion, if we look at the CO2 emissions associated with a block, about 82% comes from cement, right? That's like all concrete. A large number comes from there. 5% is due to the other raw materials, the aggregates and that. It'll be higher if you have manufactured lightweight, but in normal circumstances, it's low. And about 13% due to plant operations. Our contribution due to plant operations tend to be more than a ready-mix facility because we just don't make it and dump it. We got to have another machine. We got to take them. We got to vibrate them. We got to put them in curing. We got other things there. But the vast majority of it is due to the cement. And as a rough estimation, just ballpark, right? On the cement, about half of it's from the chemical reaction. You guys know this. That's why we'll go through it quick. About 40% is the energy you need to heat up the rocks to make it into clinker and cement, and 10% is other plant operations. If you look at it, you guys know you got a kiln. You put limestone, clay, silica, some iron-based compounds in it. They come down, they get heated up by the hellfire, right? During that, we dehydroxylate the clays, we decarboxylate the limestone. Here's a little simple thing of it. We just look at the limestone. We drive off the CO2. Then the calcium oxide combines with the silica, the aluminum, the iron, ends up forming clinker. Clinker gets ground up and some gypsum added, and we end up with cement. So we've driven off a bunch of CO2, all right? Yeah, we release a lot, but it can be reabsorbed once we put it in service. We call that carbon sequestration or carbon uptake. The calcium hydroxide carbonates first, and then the CSH gel binder will carbonate also. Again, you guys all know this, I'm just doing it quick. So you take the clinker, it's now made into cement, you add water and aggregate, you form CSH gel and calcium hydroxide as an impurity. And then when you get exposed to CO2, and the CO2 can get into the concrete, you reform limestone out of the calcium hydroxide, and then you get other carbonated species, but it's in there permanently, unless your building gets above about 550 C or something, but then you get other problems. Sequestration, wet cast sequestration, it's generally fairly slow, all right? And it's because of the lower permeability and lack of interconnected voids. This is phenolphthalein in here. The pink area is not carbonated, high pH. You can see this thin carbonated layer at the surface. On the other hand, for block, these are face, so you got a face shell, right? That's that piece in the front. We take a piece out of there, you'll see, and then we cut a slice. So this is from the top to the bottom of that face shell going across, and you can see that we have little carbonation at 4 weeks. By 3 months, we've got more, and by half a year, you got a lot more. And that's really due to the high permeability and the abundance of interconnected voids. There are numerous carbon capture, accelerated carbonation, and related technologies in use and coming out now, and they're actually quite exciting, and we see a lot of them. Manufactured concrete units is the place that they want to be used, right? They make them. We've got a contained chamber. You can cure them. I mean, it works a lot better than trying to take it out on your slab, right? So we see a lot of that. And while that's a great thing, and we've known that the concrete carbonates, we didn't really know what's the natural rate. So to do that, we undertook this research, but we look at it to generate a baseline. We determine the carbonation potential and the rate of carbonation. So the carbonation potential, I'll also do this fairly quick, is the total amount of CO2 that the cement could reabsorb if all the calcium hydroxide gel reacted. And you can calculate that for a particular cement. The way we did it in our paper is you get your cement phases, you got your C3S at the top, your C2S that reacts, forms gel and some calcium hydroxide, and then also the aluminum phases form some etronite and give off some carbon dioxide, or can give you these phases, all right? Then those phases, when exposed with carbon dioxide, the calcium hydroxide goes back to calcium carbonate. The CSH gel carbonates and gives you a carbonated gel. And then also the etronite, through a series of reactions, ends up absorbing some carbon dioxide. What we did is we looked at all the cements, and we would find out what we would use to get the Bogue equations and get an idea of what its composition was. And then we'd go through and just to give you an example here, this is this C3S. We did a mass balance. So we took the components of it, we added water that you needed the water, you get a total, then you form gel, you form some calcium hydroxide. Okay, so you can calculate that for any of the phases, that's those carbonation reactions, and then that comes over And what we ended up doing is, we got 3 calcium hydroxides here. We multiplied it by the amount of the C3S phase. We got 23.5%, and then figured out that could take up, 14% carbon dioxide. It also formed gel, and that gel then goes down here. We won't go through this whole thing, but you end up with something like this, right? So the calcium hydroxide from C3S, C2S, the gel comes down, the gel gets carbonated, that comes up here, and then also the aluminate phases go here, and we get a total of about 42.9. For all the cements in our thing, it was about 42.4. To compare that with like what you guys do, looking at the calcium, no, it makes sense. Looking at, or the calcination amounts that you get from the cement companies, this is about 90% of that, okay? That's more assuming that taking all the calcium and it all carbonate eventually. We kind of went it at fundamentals. So when I talk about this, our numbers, we're saying our potential is a little bit lower. We undertook some research starting in 2022. There's a paper that we put out in 2022 in ASTM. We collected samples. We used TGA to analyze them. And then after correcting for the CO2 bound up in the raw materials, we could get the net amount. This is important. This is really not all that easy. You got to take care of it. You cannot use TGA for limestone aggregates, but you'd be surprised that even for regular non-limestone aggregates, they will have impurities of in the order of 0.5 to 1.5, 2% of carbonate. And because there's so much in it, your background ends up being a very significant size compared to what you're actually trying to measure. So it gets pretty tricky. You got to be careful of what you're doing. What we did is we get these block. We just stored them outside, right? So this was a first shot at it. This was rough and ready research, and we just stored them outside. And at various ages, we'd take a block, we'd cut out a piece of the face shell like that, boom, boom. We'd vacuum seal it, send it to the lab. When it gets to the lab, they go and they'll open up the bag. They'll take a slice out of the middle. They'll take that slice, they'll dry it, grind it, and then run TGA. Here's a idea of or some preliminary test results. These are expressed as a term of that potential. So even at you see, all these represent different sets, and you can see there's a lot of noise in them. That's because, one, we didn't have so much money, so we only ran single samples, but also that background effect, right? I mean, if research was free, we would have run these in triplicates and they'd be tighter. But amazingly, the average gives us a very good line. This is a logarithmic line, R squared over 0.99. I think some of that, given the noise, is something called dumb luck. But there's something there, and it's real, right? We're going to be doing more research to get in on it. But, 23% of potential sequestered at 28 days, 40% at 6 months, 2 years. This is 43. That should be 53. Sorry about that. We figure in 5 years we'll be out to 60 if we extrapolate. Extrapolation is always a dangerous thing to do. But, and we think we get out to about 75% of potential. We think that's about the limit because we do not disperse the cement like you do in wet cast. We just don't have, a good 25, if we hydrate 75% of the cement, we're lucky. 25% sits in agglomerations and never sees any water, and then it won't carbonate. All right, give you an idea, what does this mean? Here's an example. We took that 82% due to cement, right? 5%, 13% there. This is one particular producer's block. Their whole carbon emissions is 200 kilograms per cubic meter, all right? And we just split it up by the percentages. And here, this chemical reaction part, this is the part we can recover by sequestration. At 28 days, 23% of that has been, on average, has been recaptured, right? At 6 months, we're talking 41% of potential, 17% of the total emissions for the block, but 41% of the potential. 1 year, 47, 2 years, 54. Okay, so that just gives you a visualization of what we're seeing. Compare it to wet cast. Wet cast, we got a 4,000 and 3,000 PSI mix. This is using a calculator and looking. Now this is a 10-inch thick slab, which would be used in the same applications as our block. If it's less than 10, obviously this will go up a little bit, but you can still, you're talking 2-3% after 2 years. You're not talking 50%. Here's just kind of a comparison. You see the block over here, then you got the 3,000, 4,000 PSI concrete. The bottom is the concrete plant and other raw materials. You see the block's a little higher because it's a more complicated operation. They got more things they got to drive. Then you get the cement. You get the energy part of the cement, and then the chemical part that you can sequester. Ready mix starts out higher, and they don't drop as much. We drop a lot more. So we're not against ready mix at all. But what we are saying is, as far as carbon sequestration, dry cast has got some advantages. That's what we've done. Now, where are we going? We're partnering with the MIT Concrete Sustainability Hub. They've gotten a grant through our foundation to model all this data, okay? We're going to start with the standard, European model of uptake. You've got a carbonation coefficient, right? Times the square root of time. It gives you a depth of carbonation. UTCC is the ultimate amount that you could carbonate, and that's where we're like 10% lower than what was typically used here. And then there's the degree of carbonation, which others will talk about more, but that has to do with a lot of things, including the exposure of it. Is it painted? Is it covered? Is it buried? And the relative humidity and a bunch of other aspects. We're going to start with that, but we're going to build off it. But it's going to be tricky because the classic model addresses carbonation only in the use stages, B1 through B7, right? It says here, that's what we're talking about. Because, look, a ready-mix truck, how much can you have? Your gate's your gate, right? I mean, you put it in there, the thing drives away, gets to the job. We store them in the yard, and the reason that you see such high numbers, those are 28 days, they're typically stored on the yard 3 weeks, a month, longer than that. We use 28 days as a reference number. But if you think about it, they're little chimneys. They got these little elements, they're hollow. We stack them on top of each other. They sit on a pallet. Air gets all the way through them. I mean, you cannot not expose them to carbon dioxide. So the thin elements and that chimney effect gives us that high uptake in the A1 to A3 stages, right? So that may be, the other thing that's happening in the early stage is we're in the active hydration state because we're producing calcium hydroxide, especially from the C3S. If we went back to those reactions, you'll see that for every molecule of CSH gel that you get from C3S, you get 3 calcium hydroxides. For C2S, for every molecule of CSH gel, you only get 1 calcium. So this was actually a big revelation. I worked for an admix company for years, and this was a big revelation that helped explain to us why we see all the early age. We tell people cure them and get them as far down the curve as possible because you want to get that calcium hydroxide exposed and carbonated, then it'll be tied up, right? So this is kicking out more calcium hydroxide. In the early age stuff, you can't carbonate it until it's produced. So it isn't a steady state kind of thing. It's going to be interesting. How's that going to affect the K values? That's why we went to the guys at MIT. They got to figure that out. So wet cast concrete is fairly homogeneous with a micropore structure of the cement. Maybe not the surface. There'd be a little bit difference at the surface, but generally you know, you're talking about the capillary voids in the paste and mortar, while CMU has another level, the macro interconnected voids, right? So if you look at it, we've got these huge highways that the carbon dioxide can get in, and then there's the paste. So the issues that ready mix looks at for permeability are not as much for us because we have this macro permeability on top of it, but how is that going to affect the K values, right? They may change over time, I don't know. And because dry cast concrete is lacking water, we can't disperse the cement. And you know, I would estimate 20-30% of cement is agglomerated and not hydratable. I made that word up. So I'm thinking that how does that impact our DOC values? So I think what we're going to find is that for DOC, we're going to end up, you know, this can cover a lot of things. Exposure conditions, the fact that, you know, we don't disperse the cement. There's a lot of things that can go into that value. Let's see what we find. So what we're going to do, what we have done is early age tests, 1 to 28 days. Went to a producer, made a lightweight set, normal weight set, sampled them at 1 day, 3, 5, 7, you know, sealed them on the spot, checked those. And we've got some of that, and this is still coming. And then we also did profile testing of the face shells. This was from advice from the guys from the CS Hub, was to model it better, it'd be nice to know how does it carbonate from outside in. So we basically would take that face shell, it's about 35 millimeters, and we turn it sideways and cut off the first 0 to 6, the crust on the outside, and then the next 6 to 12 for the next layer, and then the center from 12 to 18 takes you to the center of it. Sort of like you do chloride profiles, right? So, and chloride profiles make sense. They got an advantage in that the background there is only dilution, right? If you take a slice, it may depend on how much coarse or how much fine you have, but if you have about the right same amount of paste, you're going to be okay because you got neutral background. With us, the background's not neutral. And the coarse aggregate may be different than the fine aggregate. It's giving a signal that makes things cloudy, makes it harder to tell. So we did this, but I can tell you, we haven't analyzed it, but you definitely see it. You see the outside crust is crusty, and then it gets less as you go in. So they'll be taking that data and modeling it. We're going to start looking at concrete pavers, also using profiles. We expect those to have good numbers, not as good as CMU. They're certainly not going to have the high 28-day ones because they're stacked in a stack and they're all on top of each other. The top layer will, but the other layers won't. But they'll probably still be significantly more than wet cast. So we're going to do that. Once we get the baseline modeling is complete for the work, we'll look at the effective exposure conditions. You know, build little wallets, paint them, stucco, render, other things to see how that affects DOC. We're working towards building a model for CMU the same as we have for ready mix.